personal interactive software like STAR was unknown outside the research facilities in 1978, the year Dandelion was started. Apple Macintosh began to catch up, perhaps, to STAR's capability about a decade later. Microsoft Windows took almost 15 years. Inside Xerox PARC, however, we were quite used to this level of creature comfort. At SDD, a Xerox product group spiritually attached to PARC, almost everybody had an Alto. First built here at PARC in 1973, Altos furnished most of the computational horsepower for our culture. We had email and FTP all over the world via the ARPANET, computer-aided impressive office automation and software development tools, and computer-aided design facilities that took us from schematic to prototype nearly automatically. Our mission at SDD was to take some or all of this to the world, except we were going to redo it all from scratch. Alto was mature, and there were about 1,000 machines in use in 1979. Basically a 16-bit machine, Alto had a 600 by 800 pixel monochrome display arranged vertically like a sheet of paper, a 3 megabit Ethernet, a removable hard disk, and up to 512 KB of RAM. Alto was implemented in small and medium scale TTL logic. The CPU was microcoded, and all micro instructions were completed in 170 nanoseconds clock cycle. That's about 6 megahertz. Main memory cycles were about 1 microsecond, and by running 32 bits wide, that gives a total memory bandwidth of 32 million bits per second. In addition to emulating various instruction sets, microcode in the Alto was also used to implement much of each peripheral controller. The hard disk controller had, for example, only a 16-bit word buffer. Since in those days disk data rates were 1.5 million bits per second, microcode could leisurely read this buffer once every 10 microseconds, and small buffers meant low cost. STAR was to be much more powerful workstation. STAR's display was to be 1024 by 800 pixels, some 2 pages compared to the Alto, and consume 51 megabits of memory bandwidth. Included too was a 10 megabit Ethernet, up from 3, and 10 megabit disk drive. In addition, STAR's application software with overlapping windows and multiple fonts, and the Pilot multitasking virtual memory operating system were both written in Mesa, and they were to be emulated by this same processor at the same time. Alto, in short, wasn't nearly fast enough. I had studied our situation for my boss, Bob Metcalf, one afternoon, and was talking with him one afternoon in 1978. I was lamenting the problems we faced for STAR to build such a piece of hardware that would support such a thing. Bob's mind was wandering in the way it did when he'd already gotten the point. But he looked at me and suddenly and said, "So what are you going to do about it? Just sit here and whine?" SDD had no charter to do processor hardware. The last machine I personally designed was my homebrew 8080 in 1976, and I was at the very bottom of the SDD org chart. My coworkers, Roy Ogus, Ron Crane, and Robert Garner, were working on the new 10 megabit Ethernet. Robert had heard tell that Butler Lamson had sketched out the design of a new kind of CPU on 7 sheets of yellow paper. Butler's idea would make it possible to build a high-speed machine with relatively small I/O controllers. Alto had been based on the 74181 accumulator chip. Butler's design, which was later called Wildflower, because they were expected to come up everywhere, used 4 2901 4-bit CPU slices. He had a preliminary data sheet from National Semiconductor which convinced him that the machine could be built with 100 nanosecond cycle time and a 300 nanosecond memory cycle. That would be a 10 megabit machine. Best of all, Wildflower's design could guarantee memory latency for I/O controllers and get us the speed we wanted with Alto's simplicity and low cost. The genius, really, of Butler's design was the concept was to synchronize the scheduling of microinstructions not only with the main memory, but also with peripheral controller microcode. Microprocessor tasks were scheduled in 3 instruction groups called clicks, and each click, microcode had exactly 3 microinstructions and 1 memory access. Clicks were arranged into a round, with each controller able to demand only a fixed number of clicks. In Dandelion's case, there were 3 clicks per round, 5 clicks per round. The disk controller had 1 click per round assigned, so the hardware for the controller could be designed knowing that 1 memory access was available every 15 clocks. Clicks not required by the controllers were given to the MESA interpreter. The scheme gave low-cost controllers, DMA, microcode-based virtual memory, and complete flexibility for the design of MESA's byte-coded instruction set. Another way of looking at Wildflower's architecture is that the CPU acts like the system bus in modern machines. One addition we made to Butler's design was the addition of an Intel 8085, which we kind of stuck in the side. And it was to manage all the low-speed I/O, such as keyboard, mouse, serial communication, floppy disk, and real-time clock. The 8085 also took care of the job of initializing the main CPU to put it into operation so that we didn't have a huge amount of logic to support that function. So as a result, we ended up with an early dual processor system. Both Bob Metcalf and Dave Liddell were ready to be behind us on this adventure, but they needed a document and lots of slides to support our claim that we were doing the right thing. And to reinforce what Dave's just been talking about, this is the environment, the same period of environment he's talking about, and the kind of, as Dave was saying, no possible way of projecting this, interpreting this back from the current environment. In those days, things were very simple. Microprocessor technology was not in the state that it is now by any stretch of the imagination, and the personal computer, as I say up there, was hardly such an animal. Clearly, our only choice to achieve STAR was a custom processor. Dandelion was an order of magnitude beyond anything currently available or envisioned for the near future. By the way, we picked the name Dandelion because Park had been picking project names after very aggressive beasts. Notice the aggressive beast hidden at the end of a common wildflower. Dandelion's inception came at the end of the bipolar era. Motorola 68000 was introduced the next year in 1979 and signaled the end of bipolar machines. CMOS speeds and densities grew very quickly from then on. Dandelion shipped in 1981, the same year as the introduction of the IBM PC. The Apple Macintosh, the one that shipped in 1984, was also started that same year using the 68000 as a CPU. The team on Dandelion, and I'm going to actually put up a slide while Robert Garner is coming up to show the people that were involved in the very earliest part of that design. They were a very remarkable group. Our challenge was to have a picture on the screen by Christmas of 1979. This was accomplished by feeding the output of a scanner into memory. Between 1978 and 1981, while the workstation was moved into production, the design was enhanced to support file servers and print servers. So here's a look at the people, and we'll get Bob Garner to come up and show some of these wonderful pieces of hardware here.
Now, I think actually many of the people on this list are here. This feels a bit like a reunion. For me, it's been going back and reawakening parts of my brain that I thought were gone a long time ago. It's been quite an experience. So thanks, Bob, for that introduction. I'm going to do a little hardware show and tell. I'm going to try to set some context as well. You heard from Dave Liddell how this was an era of machines that are totally different from what we know today. And so I I found some old slides in an old box and had them scanned in, and I'll show you up here to give you a little bit of a feeling for what the context was like. Now, one of the, I think it was Gordon Bell who noticed, who remarked many years ago that the design of a machine is based not only on its architecture, but also on the financial and the cultural aspects of the organization that builds it. And this was nowhere else true than here at Xerox. And at the time, well, actually today, a very powerful computer fits in our pocket. You know, my 10-year-old understands that. But in the mid-1970s, a computer of comparable performance, you know, if you inadvertently bumped into this thing, you would smash your nose. So, you know, what today fits in your pocket looked like this in the mid-1970s. And these were the real computers. These were the ones that we were all supposed to aspire to and build, you know, coming out of school. Not these little things you can put in your pocket today. So this was a much-loved machine, the PDP-10, 36-bit machine, a little under 2 MIPS in performance. What I like about all this is everyone now knows these terms. And about a megaword of memory, not a megawatt of power, but about a megaword of memory. A very much loved machine. The designers of the Star software would have loved to have had hardware of this power, but the technology wasn't quite there. Now, a machine that was a little closer was the PDP-11. This is the Model 60. It was a 16-bit machine with a little more than half a MIP of performance and a 1/4 megabyte of main memory. And it turns out these features were almost precisely what the Star designers were looking for in performance. Now, the only side effect is that it's not going to fit under your desk, obviously, so something had to be done. Notice Dave referred to the two very sexy I/O devices on the side there, the terminal, the character terminal, and your own personal printer. So this is kind of what we wanted, but still it was a little too big. So what made the Star hardware unique? Bob talked a lot about this. Really, it was based on the Alto. The designers here at Park on the Alto realized that really what they were designing was, in essence, an appliance. I called it an office appliance here. You know, these days we hear about computers as appliances, but I think this is actually the first example because it did a very fixed function, a very simple fixed function, not a real computer opened up to the user. So one of the first observations the researchers at Park made was it didn't need a general purpose universal I/O bus. Not necessary. And those universal I/O buses were in the PDP-10, in the PDP-11. But you didn't need that in this system. In fact, if you wanted to expand functionality, you did it via the Ethernet. So this was kind of the breakthrough idea that led us down this path. And so again, like Bob talked about, it allowed us to have very tiny I/O hardware. In fact, most of the I/O operations were done in software, in microcode. And basically it gave us state-of-the-art performance, just as good as those previous mini computers, but at 1/3 of the power, weight, and cost. So the Star was actually a tremendous achievement for the time that all of us are very proud of. And Bob talked about this, and I'd like to show a picture of what it was all about. Butler Lampson basically, and some of his cohorts here at Park, came up with this idea of reworking the memory system so that the I/O devices, so that basically it was divided into 5 slots or rounds, kind of like a round robin around Robin Hood's barn. And each time a device got hold of a slot, it could move 1 memory word and it could execute 3 instructions. So this shows the 5 slots, 1 for the disk, 2 for the Ethernet, 1 for the display, and 1 for the slow I/O. And so this guaranteed that if a device needed to access memory, it always knew it could get there within 2 microseconds. And once it got there, it would always get guaranteed bandwidth, 1 megabyte per second worth of bandwidth. So this was actually a correct by construction hardware design with respect to the I/O. As long as that box ran at the clock rate it had to run at, the I/O was going to work and not have one of the terrible side effects of many of those mini computers had at the time, which was when too much I/O happened, they tended to drop data on the floor. So this was a very innovative design, correct by construction, which is a phrase I hate, but was actually true in the case of this machine. We knew it would work as long as it met the cycle time. So I'm going to do a little show and tell. This is where we get a little physical here. I've already got my fingers poked several times in the back of these boards. So this was the CPU card for Star. On the top, it's 16-bit wide, so there are 4 4-bit bit slices from AMD, the 2901s that Bob referred to. And then on the bottom was 4,000 entries of 48-bit wide micro instructions. And all of this ran at 137 nanosecond cycle time, or 7 megahertz. All that, of course, and more fits on a single chip today, so it's kind of disheartening to see more. But it's good stuff. Okay, this is a quarter megabyte of dynamic memory. A quarter megabyte. All right, a quarter. Expensive. 8 times as much memory fits on one of these chips, if I cover up the other ones. So 8 of these fits on one of these today. These are 16 kilobit DRAMs, and today they're 16 megabit DRAM. So there's a factor of 1,000 in the number of bits per chip stored there per chip stored here. So that's the industry for you. Again, it's very humbling. I moved on to the memory. So what I almost forgot about the memory is that Dave Liddell mentioned it supported virtual memory. So even though the memory itself was only a quarter megabyte, by the way, it was nice to hear, Dave, you finally let the gate open so that the poor software people could run with more memory, because I remember it was swapping too much. But later with the 64 kilobit DRAMs, it could get up to 1.5 megabytes of memory. But it did support 8 megabytes of virtual memory, which seemed like a lot at the time. And one of the amazing things about this board is it supported error correction codes. So if there was a single bit failure, it would be corrected. And that actually was a feature that didn't show up on the PC we bought later that year. Now, the Ethernet. So of course, the first Ethernet was done here at Park, the 3 megabit Ethernet. We worked on the follow-on version, the 10 megabit. This board, even though it looks big, is amazing. The top half of the board is the Ethernet controller itself and demonstrates how small the hardware was in the case of the Dandelion. You have to realize that each of these little black chips maybe has 8 flip-flops in it, and 4 NAND gates, so really small-scale integration. So the Ethernet controller was only 88 chips, whereas in the mini computers that I had showed you, it was more like hundreds of chips. In fact, I'll never forget the VAX 11 780 Ethernet board. It was as big as your washing machine, just for the Ethernet. And when DEC and Intel came and looked at and saw our Ethernet implementation, they just about collapsed because maybe they thought we had an advantage. But so, anyways, one of the stories here on the Ethernet was, I was designing it was called the Xerox wire at the time, and the target was 20 megabits a second, and I designed a board for a predecessor machine called the D0 or the Dolphin. And I had laid out the board, and it didn't fit. So I went to Bob Metcalf, and I said, Bob, I can't get all the chips to fit at 20 megahertz. And I opened up, everyone's got, you remember the old pictures of catalogs of parts? I opened up a parts catalog, and there was a Fairchild 10 megahertz CRC or checksum chip. So I went, tail between my leg to Bob, and I said, Bob, if we run at 10 megahertz, this all fits. So that's why the Ethernet runs at 10 megabits a second. Okay. All right, now we get into some fun stuff. Disk. This was the Shugart SA1000. Which is the industry's first low-cost 8-inch disc. I'm not sure how much it weighs, but it's low-cost. It's $1,000. They're actually very reliable. The designer of this disc might be in the audience. I don't know if Joel Harrison is here. I met him recently at Quantum, and he told me lots of secrets about the disc. He said, they still work? He thought that apparently they thought that the heads would have welded to the surfaces by now. And some customer he said said they'd never buy them because it wouldn't last 20 years. Well, he's going to go tell that customer they're still working. So we had one fun experience with it, which was the disk ran synchronously with the CPU, totally synchronously. And you had to supply the clock data to the disk, and so that was tied to the Dandelion's clock. So when this system was sent to Japan, where they had 50 hertz AC motors, it didn't work. And they learned they had to replace the pulley and the belt in Japan. And so there were 2 stock versions of those for 50 hertz and 60 hertz. Now, of course, today, This is 8 megabytes. This is 8 gigabytes. Yeah, 1000x. So the software better be 1,000 times better. Okay. So now, and to be honest with ourselves, this obviously wasn't enough for a network system to store all those images that Dave was saying needed to be printed. So the Dandelion could also support bigger disks, Trident and larger quantum disks, which had to be in a housing all by themselves. Okay. All right, the display was 808 by 1024 columns, 38 frames a second, and you can't change that. So actually, when Dave gives the demo, there's going to be a little bit of flickering you're going to see because we can't adjust the frame rate on these guys. Remember, they're tied to the CPU clock. Everything's running synchronously. The innovative thing about the display is there are 32 extra lines on the top and bottom and sides, which are called the border pattern, and we could make that equal to the border pattern of the rest of the display. And I heard an interesting explanation of this. Maybe Dave can collaborate this. Apparently, in some cultures, if you have a picture of someone with a black border, it implies they're dead. So, so they didn't want to have the display with a black border. So one of the nice features about the display is that you can make the border be any color you'd like. No dead pictures. And again, I've said the Dandelion was synchronous with the display. The CPU cycle equals 7 pixel times on the display. The memory equaled 21 pixel times, and the disk equaled 6 pixel times. So it's a pretty unique machine. Had to do something about scaling it. Okay, finally the IOP that Bob told you about. So this is where we use this Intel chip. Actually, this is an AMD chip. Kind of like an uninvited guest in some sense. I mean, it was definitely okay for running low-speed I/O, but over time, I guess it became something of a Trojan horse. It could handle this board. So as part of this board, the 8085 ran the 8-inch floppy drive, which we all recognize, which has also gotten dramatically smaller these days. The 8-inch, I guess all computers had to have a floppy, even though they were networked. The other things we had on here were the keyboard controller and the LED maintenance panel, which is underneath there, which tells you what state your machine is in, and connections to the laser printer COM ports and TTY ports. So actually, it was a pretty capable machine. We just didn't tell all the customers they could take their star hardware and hook it up to a laser printer and all that kind of stuff. But the same hardware could do that. Oh, man. 800 kilobytes, as I would guess. I think the double density were 800 kilobytes. All right, so like Bob, that's it for my hardware show until my arms can't take anymore. Although I guess I could show, this was the original Ethernet transceiver. This was an evolution of the 3 megabit design. There's probably some up in the ceiling, I'm sure, still here. In fact, I'm sure there's some Dandelions probably running here at Xerox, and these machines are probably homing in on them right now. So, okay, now this machine wouldn't have been possible if it weren't for the revolutionary network design environment that had been created. I mean, I stepped out of school and walked into this environment. I thought I had walked into a science fiction novel. At Stanford, I was using punched cards, and all of a sudden, here are the Altos with their bitmap screens and networking, and I thought I was on drugs. But I wasn't, and what this environment allowed us to do was to take advantage of these tools, and we actually ran like a small startup. The one thing I don't remember are the stock options. But it allowed us to work around the clock. With email, you could say what you had done, and then when the person came in when you weren't there, could read and take over from where you left off, and we actually did. We worked around the clock, and so we actually ran this project. My father asked, how can you work around the clock when you can't communicate with people? And I just sent him an email message. What? What's that? So it allowed this kind of product, and so actually from the start of the design to having hardware running just took us a year, which is kind of standard for a complete system. And then another year to announce and ship. And the hardware, like Dave mentioned, was actually announced first as a file print communication server in November of 1980. and then on April 27th, 81 as the Xerox Star 8010 professional workstation. And I found an old slide and took it down and got it scanned. This was our debug environment. It shows, this is our favorite windmill situation where we had the 6 boards in a single station where we could access all the boards simultaneously. This was Stitchwell technology, so we could turn the board around really quickly, like in a couple hours. Remember, no software simulation environment. The Alto ran this great user debug program called Burdock, which allowed us to single step the machine and read breakpoints and whatnot. And I think that person is Dan Davies. He couldn't make it here tonight. But we were really proud of that debug environment. There's actually a person I've learned at Apple is trying to recreate this environment, so I'll let you know when he gets it running. All right, so Moore's Law has been operating since 1959. You know, the Star was, I know they sold it for much less than the list price. I just wrote the list price up there. I'm sure Dave could sell you some at a great deal. They were a little expensive. They weighed a little bit, and they took all the power out of your one core, out of your one outlet in your office. But you know, they were a third the cost, third the weight, and a third the power of a machine which really had the comparable performance at the time. So they were actually very revolutionary for their time. But you know, now memory chips are 1,000 times denser, and CPUs are 1,000 times faster. And so I have wondered whether software is 1,000 times better. But one thing I've noticed, looking at these statistics over the years, having worked on RISC machines since here, was the I/O has only gone up 10x. And so even though the processor and memory has gone up 1,000x, the I/O, the disk drives, and the Ethernet are lagging. So if you keep making the software which faults, page faults, and uses the networks, you know, it's not going to run that much faster, really. And so actually, when you see the demo that Dave will be giving next, you'll see it's actually pretty quick, pretty capable. So finally, I wanted to say, if a picture is 1,000 words, I wanted to say 1,000 thanks to Xerox. Xerox, you know, they put the investment, they put the time in, they allowed the team to be created. You know, walking into this kind of design environment was just a magical experience for everyone involved. And, you know, Xerox really deserves a lot of recognition for doing that, for allowing us to put into the marketplace a product, you know, to explore, to pioneer a product which was totally new. The new concept for a PC and a new concept for a workstation. You know, basically the world's first bit-mapped, networked PC. And 1,000 thanks go to Xerox for allowing us to do that. So that's my presentation. So next, Dave Smith's going to give us a demo.